Well, good morning, everyone. Thank you for coming here. Today we'll be talking about SiPM characterization for nEXO. But let's talk first about double beta decay. Double beta decay is a process in which two neutrons from an atomic nucleus decay into one electron and one proton. But if we look at the energy of the final state and compare it with the energy of the initial state, we see that the energy of the initial state is higher than the energy of the final state, which would violate the law of energy conservation. Which is why in the 1930s, by an amount that's called Q value, which is why in the 1930s, it was understood that the two neutrons decay into one electron and one antineutrino each, an electron-flavored antineutrino and two protons. In 1937, Ettore Majorana, an Italian scientist, a physicist, theorized a different kind of double beta decay, not an ordinary one, but one which is called neutrinoless, in which the two neutrons decay into two electrons and two protons, but no antineutrinos. This kind of process would only be possible if one of the two antineutrinos is emitted and absorbed in the same process. But for this to happen, it would mean that the neutrino and antineutrino are the same particle, or the Majorana particle, which would be a first group of leptons. The energy, the Q value energy that was carried by the two antineutrinos in the ordinary double beta decay is transferred to the electrons, forming higher energy electrons. And the detection of these higher energy electrons for the detection of neutrinoless double beta decay is one of the goals of nEXO. nEXO is the next enriched xenon observatory, which is a multi-ton low background experiment that is set to take place in Snow Lab in Canada. nEXO will use a time projection chamber filled with 90% xenon 136 enriched liquid xenon at minus 110 degrees Celsius, charge collection tiles and SiPMs to detect this kind of events. Come back to our electrons to understand how nEXO works. These electrons, these higher energy electrons, hopefully, when they are formed, they are drifted towards the top of the TPC by an electric field. As they are drifted towards the charge collection tiles, they will excite and ionize other xenon particles. The xenon is not only a good candidate to undergo an neutrinoless double beta decay, xenon is also a good candidate to allow for the detection of this kind of decay because it gets ionized from the drift of these electrons to create excited dimer states that, as they de-excite, they create scintillation light. This scintillation light is in the spectrum of UV light, and it moves through the xenon towards the SiPMs in the time projection chamber. When the light reaches the SiPMs, the time projection chamber knows the system is able to know when the reaction happened and can calculate how much time it takes for the electron to reach the charge collection tiles, and therefore is able to detect the position of the event in the chamber. Here at Lab, which is one of the groups that collaborates on nEXO's research and development, the focus of the group is the characterization of the SiPMs that will be used in nEXO. It is also the comparison of two different SiPMs manufactured by FBK and Hamamatsu, and the calibration of the SiPM using radioactive sources. The characterization and comparison of the SiPMs is a multi-step process, which includes studying its light response, studying the gain versus over voltage measurements, studying the SiPM stability in liquid xenon, electric field under radioactive sources, and studying the noise of the SiPM to achieve less than 1% energy resolution, as which would be the goal for nEXO, to be able to detect the higher energy of those electrons. Personally, as part of this team, I worked on gain versus over voltage measurements, and in particular, this is our setup. We do have a small TPC and some xenon, non-enriched xenon, that is cooled down and tested with an LED, and with radioactive sources for calibration, and an electric field generator. From the SiPM, the signal is transferred to a preamplifier, which converts it into waveforms, and also feeds the signal to an MCA, multi-channel analyzer. The multi-channel analyzer also takes the signal from a preamplifier to a shaping amplifier to create histograms. These histograms show the number of observations of peak amplitudes. You can see there's multiple peaks, and overlaying the raw waveforms, you can see that these multiple peaks happen because some specific amplitudes, some discrete amplitudes are more frequent in the signal. And that is because they correspond to discrete quantities of photons, or actually photoelectric that reach a SiPM and create specific quantities of photoelectrons, 1 photoelectron, 2 photoelectron, 3 photoelectrons. And they're shown in brighter green because they overlap. So as you would expect from the MCA, you can see that some peak amplitudes that correspond to 1 photoelectron, 2 photoelectron, 3 photoelectrons are more common. And I was tasked with analyzing this data to measure gain. One challenge that we had to overcome is that not all MCA data looks like this. This is specific. You can clearly see the peaks. Some MCA data looks like this. So can we feed them manually? We could, but probably not. The machine is able to produce enormous amounts of data, and feeding them manually would be an enormous amount of work. So I created a Python class, a tool called SmartCat. SmartCat allows for automatic raw MCA data trimming for the removal of noise pedestals and flat cradles, allows for automatic peak fitting with automatic edges detection and edges correction, automatic selection of peak numbers and grouping and peak sequence to obtain the best and higher quality and less gain measurement with the smallest error. And it does all that automatically without any user input. It just takes the files from the MCA. It also works on Grace with multiprocessing and multi-threading within a group process to achieve faster, higher speeds. It was able to handle any kind of data, all a very different variety of data sets, and we just handle them fine and get really good gain measurements, really precise gain measurements. This tool can also be used without, again, any user input, just 3 lines of code for waveform analysis. Waveform analysis is the waveforms from the preamplifier that do not go through the MCA can be analyzed, and the peaks can be fitted to find their relative amplitude and create the same kind of histogram that the MCA does create. Just a few lines of code, and the software is able to automatically understand what to do, and automatically fit the peaks, and automatically understand if the data is good data. If the gain measurement that it's getting is a good gain measurement, then it's also able to reject data and gain measurements that it finds are not good fits or not coherent or inconsistent. It is also very easy to plot, just 1 line of code, and it can produce all the plotting necessary for the analysis, as well as save all the data on backup files. Initially, the peak fitting was done with shaping filters. Shaping filters were used but would give inconsistent data. As you can see, the peaks would be fitted, but there's a lot of noise in the signal, so we would get inconsistent gain measurements in the end. So something else I worked on and SmartCat is able to achieve is function fitting of the waveforms. Function fitting is done thanks to the function that I was given by Dr. Jamil that used to work here. But this fit function has many parameters, and for the computer to estimate, to calculate and fit a function also with this many variables, it would require a lot of power and a lot of time. So a lot of these parameters must be estimated, but estimating these parameters is not easy when the data looks like this, because even the waveforms, they are not perfect. Some of them are late, some of them are early, some of them are they saturated the signal, so they have flat tops. Some of them, due to correlated avalanches in the SiPM, they will create multiple peaks. So my code, what it also automatically does, it cleans the signal. By cleaning it, it is then able to create a model by averaging the clean waveforms and get much better parameters estimates for the fit function. So there's only one parameter left to fit for the computer, which is the amplitude of the waveform, which is what we really want. Yes. We use this class, SmartCat, to work on gain measurements at different PE rates, from 0.5 kilohertz all the way up to 10 kilohertz. And we noticed that going up with the PE rates, the gain of the SiPM will decrease. And this is because higher PE rates create a higher, I think, more current inside of the SiPM due to the more photoelectrons being formed. This higher current, together with a high impedance bias resistor, will create a voltage drop that would in turn decrease the gain of the SiPM. By shunting this resistor, we noticed that this effect was completely gone, because the lower impedance, the lower resistor, would not create such a significant voltage drop across the system to create a significant gain drop. And again, this is all done with 3 or 4 lines of code, thanks to nEXO. So in summary, in my time here, I created a Python class, or actually 5 Python classes. There are groups inside one tool, SmartGAT. The first one was called GAT. That they use smart algorithms to distinguish between waveforms, and MCA data. It is able to automatically fit edges and peaks, understand the best fits or the best peaks we can get from that data set, and get the cleanest possible gain measurement in the end. And it does all of that automatically. It takes a lot of computational power, which is why it runs on Grace and multi-process and multi-threads everything. And it has enabled us to get quick and accurate gain measurements, and I'm sure it will enable the team to get gain measurements quickly and easily for hopefully a long time. And yeah, that is what I work on. I would like to thank the team I work with, but also the people that made all of this possible, both here and in Italy, from the ONAOSI and Wright lab. And thank you for the opportunities, which I think I used the right way.
Last question. Did you offer a job to him?
I wish, yeah. I heard you were doing medical career,
Okay.
but yeah.
Well,
Yeah.
before I forgot to say one more thing. Our director, Carsten Hager, is not here. Unfortunately, he's traveling, but he sent me a message to express his wishes to you all, to all the team for this, I would say, successful enterprise. Thank you very much. It's time. There's time for a question.
Yes.
I have a question.
Yeah, please.
So congratulations, it's a really great work. I was wondering, when you do the fitting, or your code does the fitting, what functions do you use, or how does the code know what functions to use? Just a sum of Gaussians, or are you doing an exponential decay, or
Okay. Yes. The waveforms or the MCA data.
the MCA?
The MCA data, all the pieces are fitted with Gaussians.
Yeah.
It will try to fit them all, but it will actually trim the edges of the peaks to actually only fit one peak. So that the edge detection was a big deal, and it really made the fitting a lot better. And it actually fits them all, and then tries different gain measurements, and we'll see which gain measurement is the best one, and one with the smallest sigma. And we'll therefore, let's say, retrospectively understand which way was the right way to take. But yeah, those are all Gaussian.
And a quick follow-up question. So how do you ensure that systematically you don't get any underfitting or overfitting, and you see like more P's or less P's, and what you're seeing?
I didn't get the first part of that.
Yeah, so how do you ensure that you're not overfitting or underfitting, and you get more P's or less P's?
That's a good question, because I can see that from the gain measurement. Like when you will get a gain measurement, it's only going to be a good gain measurement and a consistent gain measurement if you fit the right peaks. So that will automatically get rid of all the bad fits. Like if you were to fit smaller peaks in between, the system would just notice that peak would fall too far away from a good gain measurement, and would just get rid of it. So again, it's done, let's say, retrospectively. It's by looking at the resulting gain, it looks at the peak of the peaks, and like, oh, this peak is too far away from the other ones. I mean, this wouldn't make sense for this line, so just get rid of it. It's probably a bad fit, and that works so well. I mean, it was really, really good at not finding bad peaks.
Nice. Is it code public?
It's in GitHub, but not public.
I should say maybe one more month.
Yeah, it's still under development. Because like for the waveforms, there's many things that can be done and will be done. Well, yeah.
Thank you.
Yeah, of course. Any other questions?
No, I think there's not so much time. Anyway, thank you very much.
Thank you.
And think about physics, huh?
I'll be a doctor. We'll just designation is probably a Python.
Very good. Now we have Thank you.